Okay, my connection is little unstable.
So anyway,
Okay.
I was just introducing you.
Yes.
So I
So just raise your hand if you cannot hear me clearly. I will repeat it. Okay. Fine. Okay. Uh, so this is Black-Scholes Mayton's work. What you model which was proposed in 1965 by Samuelson, and then the good part of this model is that it could overcome the dispute of Louis Becquerel's model, which just used Brownian that for their work in 1973, which actually they have also found out an equation for option price as a partial differential equation and solved it, and their work was recognized in 1997. I'm since so I'm going to very quickly. Thing is that still I would recall for a particular reason, because the derivation of the Black-Scholes PD, what you see generally in literature and other texts, so those things do not work in incomplete market. But there is one particular way of derivation which is easy to extend for incomplete market. So that particular derivation I'm going to do in the beginning. Then you would be able to appreciate the method. So in the Black-Scholes, you have two different assets. You call that risk-free asset and risky asset. Risk-free asset has no stochastic term. So BT, you can think that is the wealth of the risky asset, okay, per unit. So imagine that B0 is equal to 1, then it would be BT is equal to RT, so it's like compounding geometry Brown in motion. dst is equal to mu st dt plus sigma st dw. Okay, so this fine, and this stochastic differential equation has a strong solution, almost really unique. That is st is equal to this, s naught in times e to the power of mu naught minus half sigma square t plus sigma wt. Okay, so now from this we would derive one single relation, so that would be used in the later slide. So look at this DSU. Okay, so DSU, I mean here S can be written as multiplying and divided by B. Okay, so e to the RE divided by e to the RU, but S divided by e to the RU, so that I am calling as discounted stock price, that possibly you have seen in your no, in earlier classes. Okay, so this S star, by S star I mean that this is SU divided by BU. Okay, okay, so DSU is equal to D times BU times SU by BU. So SU by BU is S star U. So and BU I am writing as e to the RU. Now this is just product rule of calculus. So when you do that, you get R times. So you first take the derivative here, R times e to the RU, and then S star U du plus e to the RU ds star U. Okay. So now here, so just we are going to cancel e to the RU, and here I have SU divided by e to the RU. The denominator and numerator this would cancel. So I'll get R times SU du plus e to the RU ds du. Okay, clear? So this time I am just writing identically, only here I am doing that simplification. Okay, this is very clear thing. One good thing about this is that here you have dst is equal to mu st dt plus some term, where mu was the drift coefficient. But here I have also dst, okay, so like increment, but here I have instead of mu I have r term, okay, and I of course do not have Brownian motion but something else here. Okay, so okay, so next I would also require another relation, the quadratic variation of S. since you have already seen, elementary stochastic calculus, you know what is quadratic variation. And then, the computational quadratic variation turns out to be just an algebra, because you can have the product rule of dt derivative here, so that dst square, if you find out, and you have the rule that dt square is 0, dt times dwt is 0, and dwt square is dt. So if you put that algebra, that rule, and then you obtain that dst square is sigma square st square times dt. So you get this. Okay. So instead of t, I'm writing u, because exactly, so that this expression I can plug in some other derivations later. Okay, good. Okay, so I would just need these two things. So derivation. Okay, so now see, there is one expression of black option price that as conditional expectation. Okay, so conditional expectation under risk neutral measure. But I really want to avoid that approach. Okay, and then that thing I would get as a consequence later. Okay, the reason that I would like to avoid in the beginning, because that gives lots of ambiguity in incomplete market. Why? Because there are lots of equivalent Martingale measure. The class of equivalent Martingale measure, okay, that is not singleton. So we are not taking that part. Okay. So for the time being, just I mean. Be patient and just forget about that part and just concentrate what I am presenting here. So let us assume the function eta. Okay, so which is defined on the time domain and the space domain. So time 0 to capital T, and space domain is close 0 to infinity here, and which is continuous, and which is differentiable in the interior okay, and that has at most polynomial growth. Okay, so we also assume that this eta is not any arbitrary continuous good function, but it has also some growth property. This is important. Why? Because eta is defined on unbounded set, correct? I mean, whenever you have a function unbounded set, then it is belonging to the class of functions, and that in that class of function, if you would like to make that space as, say, for example, Banach space, some complete nonlinear non-linear space, then you need to put some norm there. But when the function eta is on the unbounded set, then if you put supremum norm, then you essentially ask the eta should be bounded. But that is too restrictive, because we know that, for example, Coloption curve, eta is more strictly increasing. Actually, it is above the S line. Yeah? That eta of TS is more than S. Sorry, more than S minus K. Above S minus K line. So, so unboundedness. So now for unboundedness, you cannot put sup norm, but you have to come up with some norm, and then some other weighted norms, etc., are considered. So you need to have some growth property. If you have a particular growth property, so eta is bounded by some growth property, then using that growth property, you can come up with some appropriate norm. Okay, and why the norms, etc., important? Because after all, when you are going to talk about the differential equations and its solutions, you need to show the solution exists in some class of functions. Okay, and then all this analysis is very much dependent on what class you are considering and what norm you are considering. Okay, fine. So okay, and there are also other more deep reasons that why this is polynomial growth condition is being used. It has some relation with the the tail property of Gaussian distribution also. Okay. So now thing is that so we assume that eta is a function like this, and it satisfies this following partial differential equation. What you have seen in your earlier classes, as Dikantara mentioned. So I'm not explaining anything much about it. And then I'm just talking about its terminal condition, that eta capital T S is equal to S minus K plus. That means for my representation, I am only considering the call option. Okay. Uh, S minus K plus. Okay, and then this is actually a redundant assumption because one can show that one does not need. I mean, any solution of this would also satisfy this, but apparently that needs the analysis. But after you don't know that, so one needs to see that okay, what should be, because that whenever you talk about this domain, one needs to put conditions on the boundary of the domain, okay, for the existence and uniqueness of solution. Okay, otherwise you cannot get uniqueness, huh? So so here eta t0 is 0, so okay, so that is the condition. Okay, sometimes people write eta ts and when s tends to 0. Okay, but anyway, so I have defined eta on this also, so no problem. Okay, so the the above equation is referred to as the Black-Scholes-Merton PD, and we know the solution. The solution of this equation can be written as this using the CDF of normal, standard normal, we denote by capital phi. So S phi log S by K plus. So I'm not reading this part. So you have already seen this. R plus half sigma square appears here, and here R minus half sigma square appears. Okay, so now good part is that this equation has a closed form solution, and the solution you can study very easily, and you can understand that okay, the equation has a classical solution, it is smooth, etc. So it is in a classical sense. Okay, so since we have this knowledge, so we can do the following. We can apply Ito's formula whenever we need, because for Ito's formula, you need that function to be differentiable in first place. Okay, so Ito's formula here. So it is just a quick recall that if it is two variable for a function, f of ts, then you can write down it is the Ito's formula. F of 0 is 0 plus integration 0 to del of del t du, and then del s dsu. So when I write on del of del s, I mean that it is differentiated partially with the second variable. When I write on del of del t, I say that f is differentiated partially with the first variable and evaluated at usu. Here also differentiated with respect to the second variable and evaluated at usu. And here second order partial derivative with respect to the second variable and evaluated at usu. Okay, so good. So this thing, and then this is integrated with respect to the quadratic variation of s. Okay, so this is Ito's formula. What we are going to use now? Okay, so we are going to use also the relations what we have already obtained in earlier slides. That is dsu is equal to rsu du plus e to the ru ds star u. So this is very important that the SD kind of things what we have obtained here in the coefficient I have r, not mu. Okay, and then eta star eta star is what? It is just discounted eta. So eta is our solution of the Black-Scholes PD, and then if we evaluate the solution at TST point, then you get eta. Then I get eta TST, and this eta star is like e to the minus RT eta TST. Okay, so here we are now treating this thing as FTST. Okay, so treating this thing, and we are writing down the Ito's formula here. So it is of course a product. So okay, in the product form, so I have to take care of that. So then the right hand side first is 0 point evaluated at point 0. So it is eta 0 is 0. Okay, e to the power minus 0 is 1. So that doesn't appear here. And then plus integration 0 to t. So yeah, so raise your hand whenever you feel that you cannot hear me properly. I would repeat then. Okay. So plus integration 0 to t, and then first we need to take partial derivative with respect to time. So here, if you do that, what we are going to get, the minus r I would get first, and then into the minus r. So minus r times into the minus ru, and this as it is. Next, I would keep this as it is, but I would take partial derivative with respect to t for eta. So e to the minus ru del eta del t. So this is the first term gives me this usu du. Okay, so this is we call drift term, du term. Du term is here. Okay, good. And then we go to the second term. For the second term, I need to take partial derivative with the second variable. Okay, so e to the minus ru is as it is here. So del eta del s usu. And now instead of dsu, I'm going to write down this thing. Okay, rsu du plus e to the ru ds du. Okay, then the third term, half times integration z to t e to the minus ru, and the second order derivative here usu, and then instead of quadratic variation, I'm going to write down sigma square su square du. Okay, good. So now, now we do some sort of manipulations, etc., rearranging of the terms. So this is first term is as it is. Now we are trying to find out all these so far as e to the minus ru is here, e to the ru here. So this I would cancel. So basically simplification. Okay, we are going to do that. So first I am considering all the terms which are du terms and where e to the minus ru are factors are there. So e to the minus ru, if I take common, so I would have minus r times eta. So I'm writing here, and here I have del eta del t here. Okay, and here I have rs times del eta del s. So rs del eta del s. Okay, and then here I have here du also. So I have sigma square s square del 2 eta del s2. So sigma square by 2 del su square del 2 del s2. So this half is coming here. Okay, good. So the term what I have not taken care is this term. But here e to the minus ru was there, and now here also I have e to the ru. So they cancel each other. So what I have now del eta del s usu ds du. Okay, good. So we can find here 1, 2, 3, 4 terms, and all these terms do appear in the Black-Scholes PD. Basically, Black-Scholes PD says that this term should be 0 because eta is solution of the Black-Scholes PD. So eta satisfies the PD. That means this term should be 0. So that these are 0. So what I get is eta 0 is 0 plus integration 0 to del eta del s usu ds du. Okay, so this is a very nice relation what we have obtained here. Okay, and this is the key relation what we are going to use to prove that eta is indeed the option price. Remember, till now I did not talk about that I did not claim that eta should be an option price. Okay, so although I'm saying that it is a derivation of the Black-Scholes PD, but I'm starting the story with the PD itself. So that is also one reason that why people do not take this path. But there is a benefit of this. Okay, it will be clear. So imagine that I came up. I am taking the PD ad hoc. Okay, just the solution of the PD. I'm not talking about any interpretation, financial interpretation of this. And then I just use Ito's calculus. Okay, so and then we obtained one relation. Okay, then now let us see that how this relation is useful to price option. Okay, so this is the finance part. So consider a strategy pi which has which is ordered pair pi 0 pi 1, where pi 0 is the number of units invested in money market account and pi 1 is the number of units invested in stock at time t. Okay, so this is basically portfolio strategy. Okay, So now one needs to put some more additional assumptions. I'm not writing here. Possibly you have already seen that to actually perform continuous trading with this strategy, you need some sort of integral square integrability of these process with respect to the stock price. I mean, otherwise you cannot just find out the gain function. Okay, so those are the things, and also you need some adaptedness, and also for here, finite expectations. You need those, mathematical conditions, what I believe that you have already seen. So we call all those conditions together as admissible strategy. Okay, so so if corresponding to an admissible strategy pi, the discounted value of portfolio. Since it is admissible, I can construct a portfolio. So the discounted value of portfolio at time t is given by, so Vt is the portfolio value. What is that? That is very clear, because if pi 0 is the number of units invested in the risk-free asset and Vt is the price of 1 unit of risk-free asset, so this should be the total money invested in the risk-free asset. Similarly, St is price of 1 unit of risky asset, and pi 1t is the number of risky assets, where a number of purchase risky asset. So this would be total money invested in the risky asset. So the addition of that would be the portfolio value, and I am dividing by BT so that I get the discounted portfolio value. Okay, so now this is equal to pi 0 t plus pi 1 times S star. S star is the discounted stock price. S by B is S star. Okay, so that is the standard notation I'm using everywhere for star for discounted thing. Okay, so this much is very clear, pretty much clear. So I'm talking nothing other than just the value of the portfolio. Okay, so now what? So now thing is that one can write down always a function f of x, okay, using if is like differentiable function, then using fundamental theorem of calculus, that f of x is equal to f of 0 plus integration 0 to x f prime x dx. So that is the way, if f is differential, I can write down that way. Even if f is not differential, but it is absolutely continuous, I can have some almost every derivative, and then that using that also I can write down that way. So similarly, if I try to do that type of thing here, okay, for v, I would also be able to write down these as integration or something, correct? And if we do that, those type of things, then then I would get actually here 4 terms, because pi and d star t and s and d pi 1 t, so 2 terms here. Okay, and for here also, like d pi 0 t, etc. So 3 terms I'm going to get. But all these 3 integrals, except that pi 1 d star u, other things like s star d pi 1 and pi d pi 0, those integrations, those should be 0 if you restrict yourselves to self-financing strategy. That means that value of the portfolio can change only via change of the underlying assets value. Okay, so what you do when you reallocate the fund, you just take and sell something, and then exactly that money you use for purchasing another thing. That means your change in the portfolio weight, I mean, this pi 1 pi 0 are like investor unit weights. So these weights are not free, you do not have full freedom of changing it. You need to obey certain things, and that condition, what you obey, that condition turns out to be the sum of those integrals should be 0, and then you would get that this left hand side would be just integration of only this term. Okay, v capital T bt is equal to v0 plus pi 1 u ds. Okay, so self-financing strategy condition implies or forces you to obtain this, and this is very nice. Okay, I mean, I have colored red and blue here. No, there's a very particular reason why did I color this thing. Is that for option pricing problem, Nothing about V0 and pi 1, correct? Because V0 is the initial capital. Initial capital, the writer of the option gets by the premium. So that is the option price at time 0. So V0 is the unknown, is not known. And pi 1 is the strategy to replicate okay, the claim at the end. Okay. So pi 1 is the hedging strategy. So this is the pricing problem, this is the hedging problem. These are unknown. But this blue color, this is known. Why? Because if I would like to hedge the option, I know that what is the terminal claim. And terminal claim should be my terminal portfolio value. If I am the writer of the option, then I should execute I should charge for premium in the beginning and continuously execute a particular strategy so that at the end my value matches the terminal claim. Then I am completely hedged. So this is known. For call option, this turns out to be S subscript capital T minus K plus, correct? This is known, but these two are unknown. But this is one equation in two unknowns. How can you solve it? Correct? Okay, fine. So we have obtained this thing. Now let us see this again from, and then actually if I say two unknowns, it will be actually underestimating the problem. Actually there are infinitely many, correct? Because this is the whole path, this stochastic process, whole process is unknown, correct? So here initial thing, and it is like a continuously some stochastic process you need. Okay, yes, any question? Okay, so I continue. So now we go back to the result. What we obtained in the last slide. There we have seen eta star, that is eta by B. Okay, so the last slide says this: eta star is equal to these two terms. Here I have some integrand and d star. So it, I mean, matches with the thing what I have just obtained. So and then there I can allow small t tends to capital T, because eta is continuous, so this left hand side converges somewhere. Okay, it is, so this is there's no problem about it. And here on this also, so this S, I know that okay, it is it is a nice semi-martingale, and then then this the eta has a very nice property that del eta del S turns out to be bounded. So these are the properties what you can obtain by analyzing the PDE. No financial interpretation is required. So now with this you can see that okay, this integral, okay, this stochastic integral is also a continuous process, so it is continuous. Okay. So since it is continuous, you can allow small t tends to capital T. You get that thing. So we do that. We take small t tends to capital T, and then left hand side we get S capital T minus K plus divided by dt. Okay, and right hand side we get eta 0 is 0 integration 0 to capital T del eta del S is this is the partial derivative. This is the second variable U S U ds. Okay, so now we compare these two things. So what is this? So here basically, like you are like driving. Okay, you need to reach here. This is your destination. What should be your initial position and what should be your maneuver? And here you are getting that if you get, I mean, if you start with this real number, this is a positive real number, right? Because eta is a solution of the PD and it is positive. All this non-negativity property, everything is there. So here you have this initial thing, and that function eta, if you take del del S of that, this is partial derivative of first order with the second variable, you get another function, and that function you evaluate at point USU, you get a stochastic process. So you get some stochastic process, and then if you integrate that, and then what you get is eta capital TST by BT. But eta solves the PDE, and that means it also satisfies the terminal condition. Terminal condition of eta is here that it should be S minus K plus. Now, if S is replaced by ST, I should get ST here. So, so here eta TST is ST minus K plus. But this is, the numerator what you obtain here is basically the terminal claim. So, so what you have obtained is that the terminal claim is possible with this as a premium and this as a strategy. So that's it. That is the solution. So by comparing both, okay, self-financing hedging strategy for call option is that your pi one, okay, pi one what we have started with, okay. Okay, the pi one is this partial derivative, and pi zero you can of course obtain from here that Vt is equal to I mean V star is equal to pi zero plus this. That means pi zero is V star minus pi one star. So that is the thing we do. The pi zero t is equal to VTST by BT minus pi, because this is my now Vt, because everything would run this way. So we have solved the Black-Scholes PD. Okay, so and then by doing that, we also now validate, yes, eta, the solution of the PD is giving me the option price. So eta itself is so the PD itself is the option price equation. So you get all the answer to all of your questions from here. Now I move to the Markov modulated thing. So of course, this thing, this thing is easy to generalize. Okay, that was the idea behind, the Foreman-Schweizer decomposition. So keeping the drawback of Black-Scholes model, so people, try to generalize the model. So in the Black-Scholes model, your sigma values are constant. So you allow that to change, and then you can allow that to change in many different dynamics. So you can allow that to be also another, like, diffusion process, which is non-negative. Also, you can just simply, make that as, as a Markov chain. Okay, that is the simplest stochastic process. Okay. So here we are talking about simplest stochastic Markov chain. So here we introduce a new Markov process that we call X with rate matrix lambda. And you know what is rate matrix, correct? So the row sums are zeros, correct? And then XT is modeled to present hypothetical state of the market at time t. And R, the interest rate, you can also allow that to depend on X, or you can keep it as insensitive, okay, up to you. And then sigma also you are keeping as a function of xt. So now sigma is not a constant, but as a function of a Markov chain. So it would change over time. So now, as a consequence of this model, what happens that the market is incomplete. So I'm not giving the proof why this market is incomplete, but intuitively you can understand for completeness. What is completeness? That every contingent claim here can be reproduced or replicated using self-financing hedging strategy. Now, if you have more randomness in the market, that means some randomness are there which you cannot trade. Okay, so for replication, what you do, the uncertainty comes from stock, but you start investing in the stock, and then you cancel the randomness by investment. But X is another randomness what I'm introducing, but I'm not allowing you to invest in X. This is stochastic, just the space of the underlying state. So here, this is not an asset. So this you cannot, hedge. I mean, there is no certainty that you can hedge. So in principle, okay. So I'm not proving here. In principle, the market is incomplete. Okay, so and then we are actually at the end. You would see the proof that it is actually incomplete. So the market is incomplete. Okay, so that means I know I cannot start solving the problem in the setting of complete market. Okay, so I have to be flexible. I have to allow me to start something where the theory or the derivation works for incomplete market also. Okay, So arbitrage free option price is not unique, and every contingent claim may not be attained by a self-financing strategy. Now here you have two different valid paths. Okay, one is that you remain you restrict yourself in a self-financing strategy only because you imagine yourself as the writer of the option, and then you see that you are in a danger because by uh, investing in the risky assets you cannot hedge yourself, so you can restrict yourself on a self-financing strategy and check whatever you can obtain at the end, and that random variable may not match with the claim, but try to find out your strategy such that on an average that matches with the claims average, and then basically your end result, what you can replicate, that is very close to the claim. How can you say the for random variable for making it close that you can actually take the standard deviation? Okay, the variance. You can say that okay, st minus k, I mean L2 norm. Okay, you can say L2 norm is the least. That is essentially mean variance hedging, because you are keeping the mean fixed and trying to minimize the variance. Okay, there is another valid approach. What is that? You you let go the self-financing thing. Okay, you let go the self-financing thing, and then you keep on injecting or taking out money in between your horizon, time horizon. Okay, until the I mean during the life of excuse me, any question?
Is there any question? If you want to ask a question, just raise your hand and ask.
Okay, then I continue.
Yeah.
Okay.
All right. Yeah.
So maybe my connection is not good. Okay. Let me. Okay. So if you. So I continue. Now, in between, if you have, so another valid approach is that in between you allow money inject and taking out of money, and then at the end you keep your you replicate the exact the claim amount. Okay, in the first approach you kept self-financing, and then at the end your objective function is to minimize the variance, minimize the L2 norm of your claim and of your replication and the claim. And second approach is that you forget about self-financing, and you try to replicate exactly the claim amount. Okay, both the approaches are okay, valid, but I am talking about the second approach now. In the second approach, it will become mathematically a little more intricate, because then you are injecting etc, then you have to actually find out the formula, the how much you are injecting in between etc. And then the very simple thing is that you do not do anything in the beginning. At the end, whatever the difference, you just inject that at the end. But then what I mean, then possibly you are taking a more risk. So I can then evaluate the performance of this strategy. So by introducing some kind of loss function. So I said, okay, if the amount of injection is too much, it is bad, so try to inject or take out money as least as possible. So then I can introduce an optimization. So then the optimization, the variables are no more a single random variable, stochastic process. So overall possible stochastic process one has to minimize. So it becomes quite mathematically complicated, but the solution becomes very elegant. So what is that? That is saying that okay, you find out a strategy such that at the end you produce the claim, but you allow non-self financing. Okay, so this is the thing what we are going to do. For that, we need to first write down the equation first. So here this dst is equal to st mu xt dt plus sigma xt dwt, because the stock price has this dynamics. So in GBM you have mu as this constant, sigma as constant. Here these are all function of Markov chain. Okay. And xt as a Markov chain, that also I'd like to write down as SD. So because that is helpful. So now that one can write down. So this is a part which you are not possibly exposed to, because you have possibly learned only the Ito's calculus for for Brownian motion, or other martingales which are having continuous paths, like MC2 in that setup. So but here, since x has discontinuous paths, so for SD I need to introduce some random measure for writing down that SD. Okay, so for the time being, we accept that for Markov chain, which is essentially a step function kind of thing, like piecewise constant functions. So that can also be written as a solution of an SD, where h is the integrand. Okay, and h depends on lambda, the choice of lambda. The lambda is the intensity matrix. So for that, you can find out this, and p is the Poisson measure, okay, with intensity say Lebesgue measure. So if time permits, I would show some simulation or some sort of visualization of these things at the end, okay, which might help. For at least for two-state Markov chain, I would be able to do that. Okay, okay. So now so then is a system of equation x and x, okay, and you assume normal thing that p and w are independent if t is the right continuous usual filtration network x and s. So then this is just a remark about incompleteness of the market. Okay, so here this is the thing what I was talking. To price an option, the writer must take care of the risk associated with a hedging strategy, but this risk is about putting money or taking money, because that essentially means that if you are a writer, you purposely need to inject money there, so that there is a loss. So hence he or she would like to seek an optimal hedging strategy causing minimum cash flow. Okay, optimal hedging strategy causing minimum cash flow, and risk minimizing, and then whatever that strategy would tell suggest that initial premium should be, that should be your risk minimizing price corresponding to that optimal strategy. Okay, so here, as before, we write down V star is equal to V by B, and Vt is equal to pi 0 B pi 1 S, okay, as before. And then this difference, V star, because earlier you remember V star was V0 plus this integration. So V star minus this integration was just V0. That was constant, that was not depending on T. But here, this is, this is the gain function, this is the discounted portfolio, and you require that portfolio to reach that contingent claim. So you adjust it by introducing some extra additional cash flow that you call C star. So C star is defined as the difference of this. Okay, so this need not be constant all over. Okay, and then since our optimization should be least fluctuation of C, so we come up with quadratic residual risk. You can take a note of it. I have not written here. This is called quadratic residual risk. So that is why residual? Because capital T is the future, T is present. So this is the residual, and you take the square. So this is called quadratic residual risk. Okay, and this should be minimized. Okay. However, this is not a simple thing to do. Okay, so instead of minimizing this, some sort of local minimizing these things is mathematically possible. So now I come to this definition. An admissible strategy pi star is said to be optimal, okay, if the And also, that is locally discriminating. This is actually a theorem that is saying the optimal is a locally discriminating, but that I kept as a bracket. You don't need to read that now. Pi star is said to be optimal if the corresponding cost C is square integrable martingale, which is orthogonal to the martingale part of stock price. MT is basically martingale part, correct? Because DST is equal to mu STTT plus sigma STDWT, correct? So this part. So S is semi martingale. So this is the martingale part. Okay, S times sigma times DWT. Okay. So I'm just writing down that. So martingale part of the stock price. So why is it so? What is the motivation behind it? The motivation behind it is that uh, the much you can do, the best you can do to replicate the claim you do. Okay, what you cannot, that part only you inject. Okay, so if you have that thing, that means that C is cash flow which you could not have generated by the investment, then basically this should be independent. Okay, independent. So that means if I take quadratic covariation of C and the stock price, okay, or maybe the martingale part of the stock price, that should be 0. That means none of the fraction of this cash flow could have been generated by investment. Okay, then only this is very crisp, and this is only the part which you actually cannot replicate, and that is your okay, that is your injecting. So this is this is the viewpoint, okay, for requiring that C star is a martingale, and not only that, is orthogonal to the martingale part of stock price. What is the meaning of orthogonal? That is quadratic covariation is 0. Okay, so that is the thing. Okay, so this is a good setting. Okay, and that is mathematically tractable, and that can be done, and this is the foundation of Forgas-Schwarzer decomposition. Okay, so that is shown here. Okay, so imagine that your contingent claim is ST minus K plus, because the Forgas-Schwarzer decomposition is very much dependent on the contingent claim, because the goal is to replicate the contingent claim. It is not like mean variance approach. In mean variance approach, you do not care about what is the contingent claim. I mean, you just do self-finance strategy, and at the end you do the optimization. But here it is very much central. Okay, so here H is ST minus K plus. So H star is the notation, it is discounted claim. So the existence of an optimal strategy, which has been introduced in the earlier slide, it is equivalent of the existence of Forgas-Schwarzer decomposition of discounted claim H star, which is the following. Okay, so this blue thing is also a theorem, is a statement. Okay, that, so what is this? Let me explain. It needs some explanation. This is your contingent claim, okay, random variable. And then you what is unknown here? This is known. This is known because this is the stock price. Okay, you know the mathematical property of this, but these are unknowns. Okay, this xi you don't know, L you don't know. Okay, and what you try to do is here that you would like to find out some xi such that you get it. But thing is that one can of course say that, okay, I can just do anything nonsense, maybe 0 every time, and then whatever is remaining to get H star, I would call that as the random variable L star. That's it. But the question is that then this random variable, okay, if you now make the closed martingale, like LH star T, conditional expectation of LH star T given FT, you get LHT possibly a martingale. But that martingale would not be orthogonal to the martingale part of S star. So any arbitrary choice of xi would not produce a random variable here, which is essentially like just a random variable, not just stochastic, just random variable. but would not produce a random variable from which would give you a martingale which would be orthogonal to star. Okay, need not be. However, this type of things is also not so very uncommon. You have possibly seen this, Kunita-Watanabe decomposition. That also basically says that, okay, how to decompose into orthogonal parts. So only thing is that in Kunita-Watanabe decomposition, here you take the martingale, but here S is not a martingale. S star is a semi-martingale, correct? Okay. Uh, Now discounted stock price under risk neutral measure is a martingale, but we are not under risk neutral measure. We are under P. P is the market measure. So it is very important that there is a reason that I actually have described Black-Scholes derivations all under the real market measure, not going to risk neutral measure. Okay, everything was done there because that is the foundation also for this four-muscle decomposition here, that we should keep stay in that. Okay. Anyway, so their work showed that that this is these are equivalent, and then only task for researchers is that to find out this decomposition. If we find out this decomposition, then this becomes the optimal strategy. Okay. So okay, so so I would also elaborate a little more about in this, in consecutive slides. So let me first finish the statement. Then Xi satisfies the square integrability condition. Okay, so here this is the condition. What is the meaning of decomposition? That this should be square integrable. This should be in the L2, so that L2 theory can work. You should be in the setting of L2 theory, and then Xi also is square integrable. Okay, so with respect to S, it is square, so that this integration is in the settings of L2 setting. Then this is a square integrable martingale orthogonal to MT, etc. There. For the decomposition one, the associated optimal strategy pi can be obtained using this. So this is not anymore very alien, because we have already seen for Black-Scholes we have obtained exactly this without this part. This was zero. The zero function, zero vector is always orthogonal to every other vector, correct? Zero is orthogonal to zero itself also. So so we have obtained, we can see that, okay, the Black-Scholes settings, which is on the complete market, that is a special, very special case here where L was zero. So you could actually produce these things only using investment. So now it is clear that, okay, this part is possibly like additional cash flow. Okay. So here pi 1 is equal to this integrand, and pi 0 is equal to v star minus this product, and v star t would be just integration 0 to small t, so capital T. If whatever you do, that would be your portfolio at time t, and portfolio value would be would give you the value of the contract. Okay, because the contract is going to give you v capital T at the end. Okay, so in between also this is the value of the contract. Okay. Now we define this H0 as sister, as I was telling that, okay, this is the this is going to give you the additional cash flow. Okay, because this is the remaining part. And now if you see that, I would share this slide to you. Okay, after looking at this, if you go back to the slide and look at the expression of discounted cost, etc., you would understand that. Okay, so this is precisely the case. And then the locally risk minimized price of a call option is given by VT. I'm writing a multiplying and divided by VT times V star T. Okay, so that here what I'm doing here is that for the first time I'm showing, because this is not essential part, this is a part which is like interpretation. So here if you see equation 1, so if you have equivalent martingale measure under which the discounted stock price is martingale, basically EMM, then under this condition of Xi, square integrability, etc., this whole integration, this integration becomes a martingale, and with a zero mean martingale. If you take expectation, it will be zero. Okay, and then this also martingale, so that will also be 0. Okay, fine. So this is the thing, and then only this thing would survive. Okay, so then h0 would be the expectation of h star. Okay, fine. So that is the thing what is written here, that mm, that if you write down, yes, is this is a martingale under P. But if you change P to P star, another equivalent martingale measure, there why should this remain as martingale? The answer is that need not be. So only if your P star is in the new equivalent martingale measure is a very special one, that all the martingales under P which are orthogonal to stock price, that is the case indeed for this setting, remains martingale. Okay, so that means it is the P2P star is a minimal kind of change without disturbing the martingale property of the stochastic process which are orthogonal to the stock price. Okay, so it is just changing discounted stock price from non-martingale to martingale, okay, in very minimal manner. So that is the notion, and that notion we are not going to use, but that is also a very popular notion, and it appears repeatedly in many texts and literature. So we are writing down that. So so this would be, since we have obtained that, okay, this right hand side will be martingale, so left hand side will be martingale, so h star t can be written as that 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 v star t is a martingale, so therefore v star t can be written as expression of vt given ft, and bt I am multiplying, so this is ft measurable anyway, so it is going inside. So this is the way we can do, and then it is just explanation, and then s and x are Markov chain, so ft can be replaced by s and x. Okay, so this is one way of writing down the option price, and vt star is actually vt, so there is option price. So option price can be retained using this conditional expectation, using equivalent minimal martingale measure. So this is this is the definition, and equivalent martingale measure p prime is said to be minimal if p prime is equal to p on the zeroth information level, that means time 0. If you restrict both the measures on f0 signal algebra, then they are equal. And f square integrable p martingale, which is orthogonal to martingale part of st under p, remains martingale under p prime. Exactly what I just explained. This is the definition. Now we come back to the actual problem of option pricing under Markov modulated market. So here, this is the equation we start with. Again, the same approach. So the derivation here actually is not actually, that we don't know the equation, we come to the equation, but we start with the equation, and we study the PD, okay, using PD technique, etc., whatever, and we obtain that, okay, this has a classical solution, etc., without any financial interpretation. When this is done, then we state this theorem that this phi, if it is solution of the PD, then this phi evaluated TSTXT would give me the locally discriminating option price at time t. An optimal strategy can be obtained exactly like Black-Scholes, that partial derivative of phi, okay, with respect to the s variable, that would give me the optimal strategy. So the solution of the problem is here, that the option price and hedging strategy both can be obtained from the solution of the PD. Okay, I'm not going to discuss about the question that why should that PD has a classical solution. Okay, so that you can find out, some of I mean, in many other literatures, actually many of my papers also, you can see that some detailed proof, many different alternative proofs you can find suitable for students to understand. And then here, so here I am not giving full details for one single reason, that here also we need to apply Ito's formula. Yeah, yeah, I think my connection was a little bad, so let me repeat again. So here also, I'm not giving full details for one single reason that for this part, you need Ito's formula, as we have done for the Black-Scholes case also. And then Ito's formula for discontinuous stochastic processes were possibly not introduced to you. So I'm not going to the details, but I'm saying that, okay, here also, if you do appropriately the Ito's formula for discount thing, then you are going to get again. So you remember that for Black-Scholes, we have obtained this thing eta star is equal to eta 0 delta del s star, but here we are going to get similarly so this is like eta, okay, eta star, okay, so eta 0 kind of thing, and here the partial derivative star and some remaining extra term. That extra term here is lambda that is coming from the Markov chain. If h lambda is 0, like Markov chain is not changing, then this difference would be just 0, etc., and this would vanish and you would get exactly this thing. However, since it is significant that regime change is there, so you would have some non-trivial integrand here. And further analysis of the PD can assure that this difference remains bounded. So you're integrating a bounded thing with respect to compensated positive random measure. P hat is P minus the P is the random measure, positive random measure, and du dz is the intensity, that is the Lebesgue measure. If you subtract the intensity, you get compensated positive random measure. So if you integrate this with respect to the compensated positive random measure, you obtain a martingale because the integrand is bounded, etc. So you get a martingale here as process with respect to u variable. U is the time variable. You get a martingale here, and then uh, this martingale, since p hat is independent with respect to the Brownian motion, and then one can show that this martingale is orthogonal to the martingale part of the stock price. Okay, so basically now if you allow small t tends to capital T, you get this equation. So where left hand side you have discounted claim at the terminal claim, discount terminal claim, and right inside you have three terms. First is the zeroth term, which is now like option price at time 0. Second term is going to give you hedging, and third term is the additional cash flow. And this is like this is the Former-Scheider decomposition, because these are in the L2 theory. This is square integrable, etc. All are true. And thing is that this is also independent and orthogonal to the martingale part. So then just obtaining this decomposition is sufficient. From there you can answer to the question of pricing and hedging together. Okay, so that is my presentation. Now I invite questions.
So are there questions or clarifications at this stage?
Okay, now Digant, you can ask me if some parts I was very fast and was not very clear. That part I can clarify maybe quickly. Otherwise, yeah, if that is needed.
No, I think this is the pace was fine.
Okay.
The only part that the students do not know is the Fulmer-Schweizer kind of concepts, which they have not seen before. But can you share one or two basic references for that?
Yes, surely. Okay, so of course I would share to give the original paper of Fulmer-Schweizer. Okay, and also maybe one lecture note, which is just 2 pages lecture note about clarifying these things prepared by some of my students. So I think that would help, correct?
Yeah, that would help.
So I would
Actually,
send
notes should be more than papers.
exactly. So I would send an email to you containing these 2 documents. Okay. And the-
Yes, yes, I will share it with the
Correct.
students. That would be great. So, okay, so I think the students will need some time to absorb the material.
Okay.
So at this stage,
Okay.
I would like to thank Anindo
Welcome. Yeah.
for making time for my class.
This is my pleasure.
And if you students, if you have questions, you can send an email to me or directly to sir, and he will help you.